Okay, we made it to the end of chapter 4, which means you guys have an exam coming up that you need to prepare for. So in this video, of course, we'll be going through the exam review assignment, talking through a few of the problems to help you prepare for that exam, help you feel like you're comfortable with everything that we've talked about so far in this chapter. I want to do this one slightly different, though, to where I want to try and cover more problems, just not go into them as deep. So hopefully in this review, we'll be able to cover, I want to try and cover, 7 or 8 problems instead of only 3 or 4, but I may not go into them as deep. The first one I want to talk about is number 2. Okay, number 2 asks you to find the indefinite integral of 10 over x plus 6 over x cubed. Your numbers, of course, might look a little different, but that's what my problem was. And looking at this one, you might be a little overwhelmed by it, but remember, I can just focus on each of these individually. Okay? And bear with me here, but I'm going to start with this one. How do I take the antiderivative of that term? Well, for this one, rewrite it. Rewrite that using a negative exponent. Okay, that's going to help me out here. But why didn't I say that about the first term? I could rewrite the first term. That would become 10x to the negative 1. But hopefully we recognize what my antiderivative is if we have it in this form. See if you can remember, what's the antiderivative of 1 over x? It ends up being the natural log of x. So, to finish this off, my first term, my antiderivative is just the natural log. So I get 10 times the natural log of x. My second term I need to use the power rule. So I'm going to add 1 to the exponent. I get 6x to the negative 2, and then I'm going to divide by that new exponent. Okay. And then, of course, since this is an indefinite integral, I'm going to add a plus c. Of course, you can simplify here, but we'll go ahead and move on. Next, let's talk about number 4. So number 4 is asking you to find your f function given f prime, so given the derivative. So in our case, my derivative is 3 over the square root of x. But then it also gives me this piece of information. And f of 1 is equal to 16. So what am I trying to do here? Well, this is still me just finding an antiderivative. So it's the same thing I did in number 2. I'm finding the antiderivative. What function, when I take the derivative of it, will give me 3 over root x? Remember, best way to help yourself out here is to go ahead and rewrite this. I can rewrite this as 3x to the negative 1/2. Okay, rewrite it like a power function, and then you can just use the power rule. But where is this going to come into play? How is that going to be helpful? Remember, when you take the antiderivative, in my case, it's going to be 6x to the positive 1/2. When I take the antiderivative, I always have to put a plus c in there. Anytime you take an antiderivative, anytime you take an indefinite integral, you have to have that plus c in there. Well, if they give me this piece of information, this is a data point. What does that data point help me do? It helps me solve for c. So that's what you're going to use that last data point for. Okay, let's move on. The next one I want to look at is number 8. And this one I do want to go into a little bit more deeply because this one can be a little confusing. So you'll notice it gives you a picture of a curve and then it has some rectangles on the curve. So that's what we're going to be doing in this problem. We're going to be estimating the area under the curve using rectangles, like we initially learned about in 4.2. Right? We're going to be using a Riemann sum, estimating the area of the curve using rectangles. But sometimes a lot of students get caught up with this graph of trying to interpret the graph and how it can help us. Well, honestly, the only important thing that comes from this graph is understanding that we're using the left endpoints, right? We're using these left endpoints to estimate my area, okay? But besides that, we can rely on everything we need to calculate this problem is given to us in this paragraph. Okay? First off, I'm given the function right here. So this is my function that I'm going to be using. So there's my function. How many rectangles am I making? Well, the graph can help you with that as well. How many rectangles am I making? It might look like I'm making 5, but you'll notice that there's one rectangle right here that's not very tall at all. So I'm making 6 rectangles. Where else can I see that? I can see that right here on top of my Riemann sum. So I'm making 6 rectangles. Okay. What's the width of each rectangle? This is also where it might be a little hard, especially if I got pretty lucky with my problem to where my rectangles ended up exactly on these grid lines, but that's not necessarily true for yours. So we might look at this and say, how am I supposed to know how wide these rectangles are? Once again, it's all given to you in the paragraph. How wide are my rectangles? That's what delta x represents. Delta x is the width of each rectangle. Okay? Well, the last thing I need is the height of each rectangle. In order to calculate the area of each rectangle, I need to do base times height. How do I get the height? Please don't try and estimate it on the graph. That's what the function's for. The function will give me the actual heights. So that means I need the height at each of these x values. I need the height of the function. Okay? So I can just plug it into my function. Well, let's think about what values am I going to be plugging in? Okay? What values am I going to be plugging in? Well, where am I starting? Since I'm using left endpoints, I'm starting at 0. Everyone's will be starting at 0 because I'm going from 0 to 300. If I plug in 0, every term has an x in it, you're just going to get 0. But what about my next term? What's the next x value that I need to plug in? Well, that's where we can go back to this. The width of each rectangle is 50. So all I'm going to do is just keep adding 50 here. Okay? The next x value I'm going to plug in is 50. When I plugged in 50 into my function, I got 2,782.5. What's the next x value I'm going to plug in? Add another 50. I'm going to plug in 100. Of course, yours is probably going to be different. Yours may not be going by 50. Yours might be going by 30 or by 40. But the process is still the same. Okay? Plug in 50. Plug in your just keep adding this amount over and over again. So next I'm going to plug in 100. When I plug in 100, I got 6,440. Next, I'm going to plug in 150, right? I'm just going to add another 50 to it. What do I get? I got 10,597.5. Sorry, that comma might get confusing, so I'll leave it out. Next, add another 50, and I'm going to plug in 200. I get 14,880. Last, right? How many times do I do this? It just depends on how many rectangles I'm making. Since I'm making 6 rectangles, 1, 2, 3, 4, 5, 6. This is my last one. I'm going to add another 50. You might be wondering, but wait, I thought we were supposed to go to 300. Remember, though, I'm using left endpoints. So this last rectangle goes from 250 to 300. We're just using the y value for 250. That's how these left-hand sums work. Okay? When I plugged in 250, I got 18,912.5. So I now have the 6 y values that I need, the 6 different heights. I have the heights of all 6 of my rectangles. How do I get the area of each of these rectangles? I'm going to multiply all of these heights by 50. Why 50? Because that's the width of each rectangle. If you want to visualize what's going on, that is what's nice about this graph, is it can help you visualize it. My width is 50, and my height, depends, right? My height depends on what x value I plugged in. Okay. So when I do that calculation, of course this area is still 0. This area became 139,125. This area became 322,000. This one became 529,875. This one became 744,000. And this one became 945,625. Remember, your numbers are, of course, going to be different, but this is just so you can see how I did my calculations. Okay. How do I get the total area under the curve? I'm going to add all these together. When I added these together, I got 2,680,625. Your numbers aren't going to be exactly the same, but they should be in this ballpark because you're going to have similar numbers. Please let me know if you have questions on this problem still. But this one can be a little tricky if we rely too much on the graph. The graph's great for helping you visualize what's happening, but in order to get the numbers, come back over here to the actual problem, and you can find the numbers in the problem. Okay? Next, I want to talk about number 10. Number 10 is simple enough. It kind of gives you a graph, tells you what the equation is. So for my example, it's just y equals x cubed. And it gives me an interval 1 to 2. And on the graph, you can kind of see that interval. And all it's asking for is the area under the curve. So all I want to just talk about with this one is, if I'm finding area under the curve, what does that mean I'm calculating? I'm calculating a definite integral. So the definite integral of my function, what are my bounds? My bounds are this interval that I'm finding the area under the curve over. So in my case, 1 to 2. Remember, always put that left-hand bound on the bottom, right-hand bound on the top. The next problem we're going to go over is number 14. So this is area of the shaded region, similar to what we did in number 10, but this one's a little tricky because if it's asking specifically for area, how do you think it wants me to count this area right here? It wants me to count it as positive area. If I just take the integral of my function, right? If I just take my integral of my function from -2 to 2, what is it going to do with that area right there? It's going to count that area as negative, right? Normally that area is counted as negative, so if I just take the definite integral from -2 to 2, it's going to count that area as negative, and that's not what this problem's asking for. It wants me to find the total area of this shaded region, which means I want to count both of those regions as positive. What does that mean? This problem is related to that my first property of definite integrals. I can split this integral up into two separate integrals. Where should I split it up? Probably where my function goes from being negative to positive. So I want to split this up at 0. So to calculate this one, I'm going to create two different integrals, one from -2 to 0 and one from 0 to 2. Well, 0 to 2 is the more straightforward one. Why? Because my function is positive through that interval. Since my function's positive, I'm just going to take the integral of the function with nothing changed. 8x plus 2x squared minus x cubed. But from 0 to -2, my function's negative. If I were to just calculate this integral without changing the value to negative, what's going to pop out? What's going to be true about my final answer? My final answer of this integral should be negative because it's going to be counting this area as a negative area. So actually, I could do that if I wanted to. I just need to make sure that when I put this into my final answer, I'm going to change that negative to a positive. I want to count that area as positive instead of counting it as negative. My other option is to tweak My other option is to tweak this integral. Since I know that the area is going to be negative, what I can do is I can just put a negative in front of it. Okay? I can put a negative in front of this integral. And what that allows me to do is, if I wanted to, I could then distribute that negative to each of these terms, and then I can take the integral of negative 8x minus 2x squared plus x cubed. And that integral should be positive. It should give me the same exact answer as the integral if I didn't put the negative, but it'll be positive instead of being negative. It's counting that area as positive area. Okay. Hopefully you guys are confident enough of actually calculating these integrals, so I'll let you guys do that to see what you actually get. But you just have to be careful with this one, and instead of counting that area as negative, I want to count this area as positive. Count that area as positive. Okay, perfect. The key to it is splitting up into two different integrals. Okay, moving on. We're not going too far. We're just going to the very next problem, number 15. This one asks you to find the area of the region bounded by the graphs. Bounded by the following graphs. Okay. Or it might say by the following functions. But it gives you y equals x squared plus 6, at least in my problem. Your problem might be slightly different. Y equals x squared. And then x equals 2 and x equals 3. So we might be a little overwhelmed by the fact that it gives me 4 functions? 4 graphs? Well, if you look closely, these are just x values. And sure, they have a corresponding graph, but the graphs are just going to be vertical lines. That's all these are. These are just vertical lines at these specific x values. So when I'm setting up my integral, since this is area, I'm setting up a definite integral. What do you think my bounds are going to be? My bounds are just these x values. So don't be confused by this. All these are giving you is just your bounds. These are my bounds. And that leaves me only 2 functions to worry about. And this is where the whole area between curves idea comes in. I just need to know which function's higher than the other function. Since this function has a plus 6, that's my bigger function. So this just ends up being the integral from 2 to 3 of x squared plus 6 minus x squared. And that actually cleans up really nicely, because what's x squared minus x squared? I'm not sure why I wrote that as negative 2. That's just positive 2. So this is the integral from positive 2 to 3 of just 6. And you can solve for that fairly easily. Next, let's talk about number 20. Okay, number 20 is back to indefinite integrals. Oh no, just kidding. It's a definite integral. It goes from 0 to 1 of 32x cubed e to the x to the 4th dx. You might look at this. So the reason why I want to talk about this one is you might look at this and think, oh no, this is integration by parts. And because it's x cubed, that means I have to use integration by parts 3 different times. And I'm going to have to use the tabular integration by parts. Oh no, oh no. But what are we forgetting? I'm forgetting the fact that this is e to the x to the 4th. I have a function inside of a function. This is not integration by parts. This is integration by substitution. I'm going to set u equal to x to the 4th. And what is du equal to? I use my differential. I get 4x cubed dx. Solve for dx, and I get du over 4x cubed. Notice I have a 4x cubed in the denominator here. And what do I have in the numerator over here? I've got an x cubed. So the x cubes are going to cancel out really nicely. And I'm left with 32x cubed e to the u times du over 4x cubed. This, of course, simplifies to 32 divided by 4 is 8. The x cubes cancel out. And I'm left with e to the u du. Now, I kind of dropped the bounds here. Don't forget that when you use a integration by substitution, you do have to switch the bounds. You have to switch the bounds in terms of u. Well, if I plug my lower bound into my substitution, if I plug my lower bound into my substitution, I get 0 to the 4th, which is just 0. If I plug my upper bound into my substitution, I get 1 to the 4th, which is just 1. So it turns out my bounds don't actually change. And then you can finish your definite integral from there. So number 20 is not integration by parts. It's integration by substitution. Next, 22. This is just an indefinite integral. Okay, 5x times the natural log of the 4th root of x dx. Okay, indefinite integral means I don't have to worry about bounds. But when I'm finished, what do I need to have at the end of my problem when I'm finished? I need to have a plus c, right? Because my answer is going to be a function, and I need to make sure and have that plus c at the end of my function. Okay. Well, we did one similar to this in class. We might see this 4th root of x and think, oh no, how do I deal with that? But remember, I have a natural log property to help with that. I can rewrite this as the natural log of x to the 1/4. And I have a natural log property that allows me to pull that exponent out in front of it. So this is equal to the integral of 5x times 1/4 times the natural log of x. And then, of course, you can combine your constants and even pull those out in front of the integral if you'd like. That looks much nicer. And remind me, how am I gonna evaluate this integral? This is integration by parts. But remember, whenever you work with natural log, you have to choose natural log as your differentiable function, which means you're choosing x dx, right? You're choosing x as your integrable function. Don't worry, things end up canceling out, which means you don't have to use integration by parts multiple times. You only have to use it once. But that's how you have to choose your u and your dv for this example. Okay? Last but not least, we've reached the end of what I wanted to go through with you. If you have any additional questions past what I was able to talk about today, please feel free to reach out and send me an email, join my office hours, and I can work through some of these problems with you. So my last problem is number 23. It's this integral of x squared e to the 2x dx. Now, in number 20, I kind of hinted at, oh, maybe I have to use tabular integration by parts. Well, guess what I have to do in this problem? I have to use tabular integration by parts. Why? Because if I try using a u substitution, the derivative is just 2, which means it doesn't cancel any of those x's out. Which means I do need to use integration by parts. And because the power here is 2, I have to use integration by parts 2 times. You're lucky. Last year, last semester, this review had the problem that had you do integration by parts 3 times. I switched it up so that you only had to do it twice. But remember, we have tabular integration by parts now to help me out. Which of these functions do I want to choose as my differentiable function? I want to choose x squared because as I differentiate that, I'll eventually reach 0, which is what I want. And then I'll choose my integral function as e to the 2x because when I take the integral of that, it only gets more complicated by constants. The constant gets more complicated, but everything else stays exactly the same. So let's go ahead and start taking derivatives. My first derivative is 2x. My second derivative is 2. My third derivative is 0. And there we have it. I've reached 0. On the other end, I'm going to take the antiderivatives. My first antiderivative is 1 over 2 e to the 2x. My next antiderivative is 1 over 4 e to the 2x. My last antiderivative, because I can stop once I reach the 0 point, my last antiderivative is 1/8 e to the 2x. Everybody okay with where I'm getting these constants? Each time I'm dividing by 2 another time. So 1/2 and then 1/4 because I'm doing 1/2 divided by 2. And then I have 1/4 divided by 2 and I get 1/8. Okay. Now tabular integration by parts tells me I can just multiply those two terms and put it in as positive. Multiply these two terms, put it in as negative. And then multiply these two terms and put it in as positive. Remember, you alternate which ones are positive and which ones are negative. And then if I try to do it one more time, of course, I would just get 0. And so I don't need to worry about that last one. Okay. This leaves me with the integral of x squared e to the 2x dx is equal to x squared times 1/2 e to the 2x. Notice how that one's positive. Minus 2x times 1/4 e to the 2x. Plus 2 times 1/8 e to the 2x. Okay, I can simplify this, of course. Just make it look a little nicer, so I get x squared over 2 e to the 2x. Minus 2 and 4, that simplifies to 1/2, so I get x over 2 e to the 2x. And then plus 2 over 8 simplifies to 1/4 e to the 2x. And if I wanted to, I could go and pull out an e to the 2x, but I don't have to. What am I forgetting, though? This is an indefinite integral, no bounds, which means my final answer should be a function with a plus c at the end. Okay. If you do not include that plus c on your exam, you will get the problem wrong, even if you did everything else right. You need to have that plus c if it's an indefinite integral. Okay, those are the problems I wanted to go through with you today. If you have any questions on any other problems, let me know. And good luck with the test.